Okay, again, double checking the sound. So hopefully we are good to go. I'm hoping no more crashes. Man, yesterday went for an hour and a half. We had no crashes. Today we've gone for like 10 minutes and we've already had crashes. What the heck? Okay, let's see. Let's keep on going here. So I am hoping, let's just make sure. I'm assuming question A we got through completely. I think that is true. In fact, yes, I know we got through completely because we were talking about the trapezoidal sum. Okay, so I was just about to remind you guys read the flashcard for for the average value theorem. So reminder, the average value theorem says the following. So it says our average value theorem is this, right? It says if we want to find the average value over a specific interval from A to B, this is our formula that we use. That is a flashcard. We should know it, right? And it always comes up. It's always up. So it's a super important flashcard along with all your derivatives and stuff. So let's continue here. I'm going to erase this for room. No, you know what? I will just make myself some more room. So let's see what we got here. Okay. Sorry, I got thrown off my game. It was going so well. I felt so professional. So let's go and set this up here. So for this thing right here, let's go and fill out the average value theorem. So we're looking for the average value over the first 4 hours. So in other words, we're looking from hours 4 to 0, and our integral is going to go from 0 to 4 of L of t dt, because they're asking for the average number of people over that period of time. Okay, so this is our setup. In regards to the setup, I'm going to pause just for a second, see if you have any questions. Okay, doesn't seem to be any questions, so let's set up our trapezoidal sum. So actually, I am going to erase my flashcard now, and the reason is I want to grab the table and bring it down so we can look at it. So, reminder what a trapezoidal sum is. We have we have two trapezoidal type things. We have the trapezoid rule, and then we have a trapezoidal sum. A trapezoidal sum is literally, hey, you have this curve. So we have this curve, and we want estimate the area underneath the curve using a bunch of trapezoids. So those trapezoids there's nothing special about them. They don't have to have the same base. There doesn't, right? So I can make skinny ones, I can make fat ones, I can do whatever I want. That's a trapezoidal sum. You're just taking your trapezoid and kind of adding them all together. When you have the trapezoid rule, on the other hand, the trapezoid rule is very specific. It says all your bases have to be the same. Okay, this is a trapezoidal sum. So all they want us to do is literally break up this thing up into 3 trapezoids. And those trapezoids we're looking at are going to go from 0 to 4. So if you were to imagine for a second, this is not going to be accurate for this one, but this trapezoidal sum might look something like, if we were to kind of graph it, we would have 1, 2, 3, 4, and I'd have 4 trapezoids. In this case, they may not, so just kind of recognize, yeah, no, that's fine. So one trapezoid has a base from 0 to 1, so maybe it looks something like this. The other one has a base from 1 to 3, so let's say maybe it looks something like this. And then the other trapezoid has a base from 3 to 4. So maybe something like this. Notice these bases aren't the same. That's fine, because this is a trapezoidal sum. All we're going to do is go find those 3 trapezoids, and add them up together. So a reminder on how we find them. In order to find the area of a trapezoid, we have to take the area of a trapezoid is 1/2 the average of the bases times the height. So in other words, for my first trapezoid, this would be base 1, this would be base 2, this would be height. Okay, and I'm going to do that for each trapezoid. So let's go and do that. Let's go and do that. So this is going to be equal to 1/4 times, and let's see what I got. So I'm going to take the average of the first two bases, so 1/2. My first two bases are 120 plus 156 times the height, which in this case is the distance from 0 to 1, which is 1. Next, I'm going to add to that the next trapezoid. And that trapezoid it's 1/2, and then the average of the bases. So for the first base, it would have a height of 156. The next one has a height of 176. Then I'm going to add to that, what is it? 1/2 times 176. Oops, I'm sorry. The last one, I forgot to put down the height. So I missed a number here, my apologies. Let's put the height, so that the height of that trapezoid was 2. So I'm going to put that in right there. And then we're going to take, let's see, 176 plus 126, and then multiply that by the height of that, which is 3 to 4, which is 1. And that is going to be my answer. I can clean it up. In fact, if you clean it up, you get, this is a calculator question, so you might want to throw it on your calculator. I don't know if it matters. It probably doesn't, but it just kind of recognize it is a calculator question. So this is my kind of my final answer, and I could do that on my calculator, figure out what that is exactly. This is actually, wait, this is, we're averaging, yep. This is the average number of people. So there's the 621 divided by 4 people. That's our average over that period of time. Okay, so I'm going to pause there. I'm going to look at, let's see, Discord. Discord asked, why did the integral go away? The integral did not go away. I just removed the flashcard. And only because I removed the flashcard, only because I just wanted room. The integral itself did not go away. This is the integral that goes, oh, are you talking, I'm sorry. I think I understand what you're saying. You're asking, why did the integral go away when I started plugging my stuff in? The reason is this stuff right here is the value of the integral. Remember, in order to find the area, the integral, we add up the area underneath the curve. In this case, I am approximating the area underneath the curve using the trapezoid rule. So I'm actually evaluating my integral at this time. So of course I wouldn't have the integral anymore because I'm doing the evaluation. Okay, let's see. So there are a couple questions coming in. All right, okay, so there's two. Question was asked, are you using the average value theorem or the trapezoidal theorem? I'm using two theorems in this one. So theorem number 1, I used the average value theorem to set up my equation, my function. That's the average value theorem. I'm then evaluating that function that I wrote up, right? I'm evaluating this using the trapezoidal approximation. Right. So yes, we did the trapezoidal sum of the average value of the function. That is correct. Are there any other follow-ups for B? Questions coming in? So the question is, what's happening to the integral? Here's what's happening to the integral. So let's backtrack just a little bit. Well, I'm not going to backtrack. Let me just kind of show what's going on here. So for right now, let's just look at the integral right now by itself. Don't ignore the 1/4 4 minus 0. Let's just look at this, okay? So we're just going to look at this piece right here. What we want to do is we want to evaluate it. So remember, this function, and again, I'm making this up. Maybe this function looks something like this. So let's just pretend it looks something like, maybe it looks something like this, okay? What we just did is we found this stuff that I did over here, this stuff right here, is giving me an approximation for the area underneath the curve. So what we did is we made a bunch of trapezoids. Trapezoid number 1, trapezoid number 2, trapezoid number 3. I found the area of those 3 trapezoids. That gives me this. So that area that I just found, that is that red underlined part. Those two things are equal. I just evaluated it. Hopefully that makes sense. There was another question is, what are the units? The units are people. So when we take the average value theorem, the units remain the same. Other questions that you have? I'm going to clean this up just a little bit here. In case you're getting things down, might make it a little bit easier to write. Okay, I think no questions that come in, so I'm going to say that we are good and we can move on to C. Oops. Let me move this. This got moved. Okay. For 0 to 9, what is the fewest number of times at which L of t must be equal to 0? Give a reason for your answer. So they're asking me, where must it be equal to 0? This is an existence theorem. Okay, they want to know where basically L prime of t equals 0. So I'm going to be using the mean value theorem here. So let's let me grab the table one more time. Actually, you know what? Can I just paste it? No, I can't. Okay. So let's just, before we go through like in an official way, let's see what we can do. So imagine for a second, let's just kind of visualize what's going on with this table right now. So with this table, so I'm going to make a quick little graph. I'm going to erase this afterwards, so I'm going to take up the whole space here. So with this table, at time 0, I'm at a height of 120. Okay, so let's say right here. This is not accurate. Then at time 1, I go up to 156. At time 3, I'm at a height of 176. Then at time 4, I drop down at 126. So think about what must be right there, right? That's a relative maximum. So there must be somewhere in this interval, the derivative has to equal 0, right? That's when we talked about graphing, when we talked about those type of things, there has to be a critical number there. There has to be a maximum there, somewhere in there. We don't know where. That's why I'm going to say mean value theorem. That's how I'm going to justify it. But somewhere there has to be a maximum. Let's keep on going. So we drop down, and then at time 4, we're at 126, but then look what happens. From time 4 to time 7, it goes back up again to 150. So again, right, we change direction. The function went from decreasing to increasing. So again, there has to be another critical number somewhere in that interval. And then finally, what am I at? I'm at time 7. From time 7 all the way on, it keeps decreasing. So again, there has to be another critical number. So we're looking at 3 critical numbers. Okay. So first off, we're looking at just 3 critical numbers. So the questions asked is, how do you know mean theorem, why not Rolle's theorem? So first off, the question is, how do I know mean value theorem? So the way I know mean value theorem is I've already kind of worked through this problem, so I kind of know where I'm going with it. So you could say I'm cheating a little bit. I know the way my explanation is going to go. So what I'm going to do in my explanation is I'm going to say, hey, look, the slope of the tangent line from here to here is blank. Okay, I don't know what that slope is. Then the slope of the tangent line from here to here is blank. So what does that tell me? Well, in the first interval, in this part right here, if the slope of the tangent line is some positive value, then the derivative has to be some positive value on the interval. I may not know what that positive value is, but I can say this because the slope of the tangent line by the mean is positive by the mean value theorem, the derivative in that section also has to be positive. Then when I move over to the right-hand side, right, the slope of the tangent line is going to be negative. So I'm going to use the same logic and say, hey, look, L prime also has to be negative. Since L prime switched from positive to negative, there has to be a critical number somewhere in the interval. That's my logic. That's kind of where I know. That's how I know where I'm going. Now, the other question was, why not Rolle's theorem? Rolle's theorem, in order to use Rolle's theorem, I have to have the requirements for Rolle's theorem. One of the requirements for Rolle's theorem is that f of a has to be equal to f of b. So for example, if at time 0 and time 3, both the outputs were 120, so time 0 was 120, time 3 was 120, I could use Rolle's theorem because f of a equals f of b. But in this case, none of these values are the same, so I cannot use Rolle's theorem. So next question is, why wouldn't all the derivatives be positive because it's above the x-axis? The reason is this is a graph of a position function. When I'm doing here, right, I'm graphing the number of people. So remember, a derivative gives me the slope of the tangent line at a point. So right over here, all my slopes to my graph are positive. Here, all my slopes are negatives. So again, when we're talking about derivatives, we're just talking about slopes of tangent lines. We're not talking about the position values. Okay, I'm going to erase that in just a second, see if you have any questions before I do, and then we can actually move on to C and actually answer it officially. There's a question coming in, so I'm pausing here. So the question was asked, when do you use the idea that when slopes are above or below the x-axis, we're talking about positive, negative. That's when we're looking at the derivative. So for example, if this graph that I just drew here was the graph of the derivative, then when we look, when we have points above the x-axis, then the derivative is positive. When we have points below the x-axis, the derivative is negative. Again, it's only when we're looking specifically at the derivative, but this is a position function. Hopefully that makes sense. Okay. Perfect. So what's being typed right now in Discord, that's exactly it. That's exactly it. Perfect, perfect, perfect. Okay, let's continue. Let's continue here. So, let's see. So I'm going to get rid of this so I have some room to work. And now I've forgotten what the question is. So I'm going to have to kind of read over to myself again. So let's see. What is the fewest number of times in which L prime of t must equal 0? Give a reason for your answer. Okay, so here's what I'm going to say. And I want to emphasize this is kind of just for me, it was kind of a hard one to put together. As you saw, I can kind of, I explain it well. I hope I explained it well to you, right? I know, very, very boastful of me, but I feel like my verbal explanation was pretty good, but the written one's for me was a little bit harder. So here's what I'm going to do. First thing is since I'm going to be using mean value theorem, I'm going to think about what are the requirements for mean value theorem. The requirements for mean value theorem, there's only two. Requirement number one, function has to be continuous. Requirement number two, function must be differentiable. So remember at the top of this thing, I said this thing right here was really important. It's twice differentiable because that tells me this function is both continuous and it's differentiable. So I can say, sorry, let's make this a little bit bigger. So L is, so I'm going to say L is twice differentiable. Which means it is both continuous and, of course, differentiable. Okay, I probably don't need to repeat the fact that it's differentiable. That's been stated. That's a known fact. The big important piece here that I stated is that it's continuous, right? Differentiability implies continuity. So that's the big important piece. Well, whether I state that it's differentiable, I probably not. Who cares? They've already stated that fact. I don't see any good reason to restate it other than just because I did. Okay, so now I can say by mean value theorem. And by the way, you can use this abbreviation. It is a well-known abbreviation. So by mean value theorem. So I'm going to say L of 3 minus L of 0. So notice what I'm doing is I'm finding the slope of the tangent line from 0 to 3, and I'm noting that that's positive, which means L prime of t somewhere in that interval has to be greater than 0. Okay, so L prime is greater than 0 for just that piece. Okay, let's keep on going. So then I'm going to look to from, what did I say? I'm going to look from 3 to 4. So I'm going to say I'm going to definitely need more room over here. So because the slope of the tangent line in this interval is negative, then somewhere in that interval, right, by mean value theorem, L prime has to be negative. So what does that tell us? I'm going to move these down. I need a lot more room here. Sorry, got distracted. So what does that tell us? That tells us somewhere, right? And I'm gonna sum this all at the end, so I'm not like constantly repeating myself. But this tells me somewhere in this interval from 0 to 4, right? It went from increasing to decreasing. That somewhere in there, there had to be a critical value. We could actually narrow that value down, but they're not asking us to narrow that interval down. So let's keep on going here. So I have found this is right here between these two. This is the location of 1. Let's keep on going here. So the next one I can say this is a little awkward to me. I want to say therefore for each one of these. So if you don't mind, I'm just going to say this symbol right here means therefore. I therefore, because this implies, so that therefore L prime of t is greater than 0. So L prime of t is greater than 0. And then finally, let's see, which means, I'm sorry, let's go there. So what happens in between these two right here? It went from L prime being negative to positive. So there has to be another critical value there. And then finally, we can say L of 9 minus L of 7 over 9 minus 7. And that was negative, right? It's decreasing. So therefore, L prime of t is less than 0, which means, again, right, there has to be a third one there. I'm going to need more room because I still haven't finished. But notice there are three critical values, and they're all being justified by the mean value theorem. I'm going to kind of sum this up a little bit. I have a little bit more to write, but before I do, because that was a little bit longer, see if you have any questions. See if that makes sense to you. Okay, then, the question is coming in. Is this question a typical length for the AP? So you mean my explanation? Maybe a little long, but usually they're pretty quick. Usually like if you look at, well, this one, okay, so this specific question was actually pretty long. This first part wasn't, but I mean, I think you'd agree the trapezoid problem was kind of long. I mean, there wasn't anything we could really do with that. This one I think was long. So usually we can get through them you can get through them pretty quickly. So usually you should be able to get through an entire problem in like 10 minutes. Now obviously I'm talking this through, but if I was just doing this on my own, I'd probably take 15 to 20 just because of the length of these explanations, but realize that the rest of the questions would probably be a lot shorter. So this happens to be a particularly wordy thing. And like I said, I think this part C is I'm probably going a little bit wordy, but I'm not quite sure how I would make it shorter and still convey what I want to say. And that's obviously the most important thing in the end is that I'm conveying what I want to say. Okay. So let's keep on going. But again, usually students, around by the time we are really close to AP, they're getting through a question in about 10 minutes. Will there be questions that take them longer? Absolutely. That just happens, period. But, hopefully not more than that. Okay, let's keep on going. So I'm going to just finish this up. So, okay. Now, I feel like this was kind of a stretch question. So what I'm going to say, I really want to emphasize this, and I feel like for a student, this is kind of a tough part. What I'm going to say is, hey, look, the derivative. So let's look at this first part right here where the first critical number was. I'm going to say, hey, look, at some point, we knew the derivative was negative. At some point, we also knew the derivative was positive. What does that mean? That tells us that somewhere in that interval by IVT, by the intermediate value theorem, I know another theorem that's been a super long time for us to see, at some point it had to be equal to 0. Okay, so I'm going to finish up writing that explanation. I'm betting you're going to have questions on IVT because it has been such a long time since we used it. But let me finish writing this explanation down, and that way I might need some space to discuss IVT a little bit. So by IVT, okay? So let's talk about IVT. Well, actually, before we talk about IVT, do you have questions on IVT? Maybe you guys are all super solid on IVT and you don't have any questions on it. So let's start with that. Are there questions on IVT or how I was using IVT to justify? So I got a couple people asking some questions here in Discord. Yeah. So both the questions are pretty much the same. They're asking, how did we go from MVT to IVT? Good question. Good question. Okay, so now that we've got this down, if you guys don't mind, so why even talk about MVT when we were going to go right to IVT? Okay, so all kind of the same question. So I'm not gonna backtrack. I want to this is perfect right here, but I want to I'm going to erase this so I can kind of address these questions. So again, if you need anything from this, actually, you know what, let me just scroll the rest of this down because I just need space to kind of answer this question. But I want you guys to realize that the answer to this question has nothing, obviously doesn't do with my explanation here. Okay, so and again, this was kind of a stretch question. I think recognizing that we had to use both MVT and IVT here, that's kind of a stretch question. But let's kind of focus on why I had to use both. So let's do the graph again, because I think visually this hopefully makes a little more sense. And so our graph kind of looks like this, right? It starts at some number and it goes up for a bit, then it goes down for a bit. Oops, not that much. It goes down kind of shortly, then it goes up again, and then finally it goes down again. And I think you guys, if we just plotted those table of values, I think you guys would agree with that. Okay, so I had to do a couple things here. So first thing is, let's think about what are the requirements. So let's work this backwards a little bit. What are the requirements for IVT? So the requirements for IVT, if you guys remember, so the intermediate value theorem basically says if you have a function that is continuous and we have some k value such that f of a is less than or equal to k, which is less than or equal to f of b. So in other words, we have some value in between two different y values. So in other words, on the graph specifically, if this was f of a and this was f of b, and let's say f of a is at, let's say, 125 and f of b was at 160. The intermediate value theorem guarantees that if I want to say is 150 between those 2 points, is there a k value of 150 between those 2 points? The answer is yeah. If this function is continuous, there has to be some c value, right? There has to be some c value where I evaluate the function at c, and that c, so that I guess it's L of c, has to equal 150. That's all that intermediate value theorem says. It says if you have a function that's continuous, then in a specific interval, then those height values have to be, I'm saying this poorly now, that there has to be some c in that interval such that f of c equals some k value in that interval. That was not the best way of phrasing it, but again, we've talked about this a lot. So see, hopefully that makes sense, what the intermediate value theorem is. So see if just in general terms, are you okay with intermediate value theorem? If you have any questions on just that concept right now, ask it. Okay, so it looks like we are solid on just what is the intermediate value theorem. Okay, so let's kind of now backtrack here. We understand what the intermediate value theorem is. Now, let's think about what I did. Whoops. I'm trying to say, I want to get rid of that red dot. Okay, I'm trying to say that somewhere here, right, somewhere in this interval, L prime of some c value equals 0. I'm trying to guarantee that value. So, and the way I want to guarantee it is by IVT. So I want to say, hey, look, I want to be able to show that, look, L prime, if you look to the left of it, L prime is positive. And I think you guys would agree, any slope of any tangent line at this point to the left of that C value, so we'll call this that C value, all those tangent lines are positive, okay? How do I know that L prime of t is positive? Well, since the secant line, right, from here to here is positive, then by mean value theorem, I can guarantee that there has to be some values of L prime that are positive. So I'm using mean value theorem just to be able to state that L prime is positive on the interval from 0 to C. Okay, then let's go to here, and I'm going to call this, so this was C1, we'll call this C2. Then I want to say, why am I using C2? Well, sure, I'll use C2. Then I want to say, hey, look, the derivative from here to here is negative. How do I know that? Well, I look at MVT again. I look at the slope of the secant line from C1 to C2, and I say, look, it's negative. Therefore, L prime is negative. So now what have I established? Well, I've established that from 0 to, let's say, C2, L prime has changed signs. Okay, so I've established that L prime has changed signs. Mean value theorem allowed me to talk about the signs of L prime. So from 0 to C1, mean value theorem allowed me to say that L prime was positive. From C1 to C2, it allowed me to say, mean value theorem allowed me to say that L prime was negative. Now that I know their signs, I can now start talking about IVT. And I can say, hey, look, since L prime of t equals some positive number, right? So we'll just, I'm going to shorthand this. I'm going to say equals some positive number. And since L prime of t, from C1 to C2, it equals some negative number, then there has to exist some k value in the middle where k equals 0, right? Because you can't go from positive to negative without passing through 0. Okay, and again, I'm using IVT to justify this piece, because as long as the function is continuous, that underlying piece has to be true. Okay, that's probably about as clean an explanation as I can give. See if you have any follow-ups. No? Okay. So the question is, why couldn't you just use IVT if they overlap like that? So the reason I can't, so remember, so IVT's job, think of each of these theorems as having a job. IVT's job is just to say, look, this k value exists. Somewhere in the interval from A to B, this k value has to exist because the function is continuous. That's all it does. It only guarantees the existence of a specific k value, which is what I wanted from the original thing, right? It wanted to know, was there ever a k value of 0? Perfect, IVT. But I had to use MVT in order to show that L prime was positive here and negative here, right? I can't use IVT to do that because now I'm talking about a slope of a tangent line. IVT doesn't talk about slopes of tangent lines. It guarantees values. What talks about slopes of tangent lines? Mean value theorem. Another comment or question is coming in, so I'm kind of holding off. Perfect. Perfect, perfect, perfect. So the response was MVT was used to set up IVT without the exact values of A and B. Perfect. These are paper. These are you really. Thank you very much. You're really totally clarifying. Probably better than I am. Excellent job. Okay, let's continue. let's continue here. Nicely done. Nicely done. Okay, let's continue here then. So unless there's any follow-up questions, I know this is a long one, okay? I recognize this is a long one, and I recognize there was a lot going on here. I can't, first off, obviously, the graph stuff, all that stuff below, that's not part of it. Um, recognize there is a bit of a stretch here. So probably, I feel like a lot of you would have recognized that there had to be three places because you saw, or if I just were to quickly graph it, I could have seen that there were three places. So that's at least a point right there. Whether you could go through the explanation, I recognize. You have to start asking yourself, how do I know these things exist? Okay, I'm talking about existence theorems. Part of it, yes, it's just practice. You just have to kind of practice learning where to recognize, different existence theorems apply, right? We only have three. Rolle's theorem, mean value theorem, intermediate value theorem. Those are the three that get used all the time. There are some other ones for the intervals, but these are the ones that get used all the time, especially on the free response. So let us continue. What is D? The rate at which tickets were sold from time 0 to 0. Probably not 0 to 0, because otherwise that doesn't make any sense. Okay, so the rate at which tickets were sold from time 0 to 9 is modeled by that function, which represents tickets per hour. Based on the model, how many tickets were sold at time 3 p.m. to the nearest number. So I liked it before, so let's do this again. So I have a question for you. Again, anytime you see a graph, a table, or a function, you should be asking yourself, is it a position, is it a velocity, or is it an acceleration function? So they gave us this function. I need to know, is it a position, velocity, or acceleration? So in the chat, if you would please type 1 if you think it's a position function, type 2 if you think it's a velocity function, type 3 if you think it is an acceleration function. So let's see what you guys think. And type 4 if you're like, I have no idea whatsoever, and that's where I stand. Got a couple 2s coming in. A lot of 2s coming in. No 3s? No 5s? Let's see. Okay, we got some 2s coming in. I agree with the 2s. It is a rate function. How do we know it's a rate function? We again look at the units. What are our units? Tickets divided by hours. That's a rate. If it was just tickets, that'd be a position. If it was tickets divided by hours, or hours squared, that would be an acceleration. Okay, so absolutely, that's just tickets per hour. That is just a rate of change. So what are we supposed to do? Uh-oh, my earphones are already running out. How long has it been? 1 hour? I only get an hour of my earphones. I'm gonna have to fix that. Okay, you guys told me yesterday that I was okay, so I'm gonna assume that you guys are still okay hearing me. And I think I think they're still actually working to a degree. They haven't completely died on me. So again, if my sound quality starts to die, just please let me know because I'll talk louder and lose my voice. So the rate at which tickets are sold was this function. How many tickets were sold? So now they are asking how many tickets are sold from 3 p.m. This is a displacement question. So in other words, they want to know from time 0 to 3, how many tickets are sold? What is our displacement? This is a calculator question. You're literally going to plug this thing on your calculator with the given limits of integration and get your value. So in this case, we're going to I did the math ahead of time somewhere because I got this to be 972.784, but they're asking to the nearest ticket. So that would be 973 tickets, period. This is just a calculator question. They're not asking you to do anything other than just evaluate. Probably a 1-point question. Okay? Oh, I didn't write down the question quite oh, you are right. I did write the thing down incorrectly. My apologies. You guys have it correctly in your packets. Like I said, I did do this math ahead of time because I didn't want to sit there fooling around with my calculator. So there should be a t here. Thank you. Okay, so again, when we plug that into our calculator, that's what we get. Hopefully you guys are comfortable on your calculators. I can, if you have calculator questions, I can answer them to a degree. It's a little hard, obviously. I do have a calculator on my iPad that I am super bad at using, but I can answer some questions on with the calculator stuff here. So anyway, see if you have any questions in regards to D. I feel like that one was fairly straightforward. Of all the questions, usually D is a bit harder question, but that I felt like was probably the easiest question they asked. Okay, so see if you have any questions. And then if not, if you don't have any questions, which, oh, something's coming in. By the way, if you guys notice, I'm kind of avoiding part D and A seem too easy. You know what? That's not necessarily true. So I'll answer the second question in just a second. But so sometimes the questions are really easy, and part of the reason they may have made this first question fairly easy was we spent so long, and they may have counted on the fact that you were going to spend a lot of time with the trapezoid question and the part C question, that they needed to make the other ones a lot shorter. So it sometimes we just, a lot of times what will happen in a question is you'll have some really easy ones and some ones that are more difficult. I agree with you. These were kind of easy, but then again, they got to get you, it should take you on average 15 minutes. If every single question was like B and C, this would have been probably a 25-minute question. And that's if you're really, busting through it. Okay, let's answer the next question is, how did you know to use an integral? How did I know to use an integral? Okay. So here's how I know to use an integral. So if you notice in the first part, they gave us, as we said, they gave us a rate of change question, right? Tickets per hour. They wanted to know how many tickets were sold. Tickets, right? That's a position. If I'm looking at the number of tickets, position. So I have a velocity function, and now I got to go to a position function. How do we do that? Oh, we integrate. Okay. Any other questions that you have on this part? No? Okay, so the next thing I wanted to, oh, another question is coming in. Also, just to kind of note, if you guys are wondering, I'm kind of avoiding saying your names just because I don't know how comfortable, I know this is definitely out there on the internet. I assume, I feel a little bit uncomfortable using your names when things are out on the internet. So just if you're wondering why I'm avoiding saying that, that's the reason why I'm doing that. I do realize that some of your names are on the live stream typed, so that I'm just kind of letting you know. That's kind of that's why I'm kind of avoiding that. So let's see. Next question was, would it ask for tickets per hour squared? I don't think it would. So that the reason being is, so that's an acceleration, and they could say, how is the rate of change of the tickets per hour changing? I'm not exactly, I mean, it would be a really convoluted question. So could they? I guess they could. Have I seen it? No. Um, I would think if I were going to start talking about acceleration, I literally would be talking about a moving object. So a line, yeah, it's kind of like a moving object, right? The number of people going in and out, that's a moving object. But I really think if they were gonna start talking about acceleration, I honestly think they would talk about some sort of something actually physically moving. Otherwise, that's really esoteric in my mind. Um, anyway, let's see. Yeah, exactly. So the question was, what would acceleration function even represent in this case? It would represent the rate of change of the line it would represent the rate of change of the rate of the line changing. I may have had too many rate changes in there. I may have just taken their derivative. But like I said, as you can see, it's awkward. It's very awkward. So I don't, physically speaking, that's a little weird. Okay. Okay. So that's that one. I did want to go over, I assume that you guys have been kind of working on the free response. I'm sorry, the multiple choice. And I did want to see if there were any questions regarding the multiple choice that you've been doing so far. Is there anything that we can kind of look at while we have some time here? At some point, as you guys know, my earphone's going to die, and I'll just have to talk a little bit louder. But again, if you have any questions in regards to multiple choice, again, I'm going to probably look at, let's say, Tuesday. I'm going to be hitting that multiple. Well, I told you guys to have the multiple choice done by Friday. So yeah, let's do this. Let's say Tuesday at 10. We can definitely focus on multiple choice. So make sure you've gotten some decent multiple choice done by Tuesday, so you can ask questions then, and we can focus on that solely. In fact, I won't do any free response on Tuesday. And then maybe Friday, we'll do the same thing on Friday. I'll also go through questions on multiple choice. That way we have a couple dedicated days to multiple choice. Because but like I said, let's just kind of hit it right now. So let's see what we can do. So again, that is question number 5. Feel free, if you are like, hey, I don't need anything from the multiple choice, feel free to, leave the live stream if you want to. Stick around if you want to. Whoa, something's happening in my house. So let's see here. Let's go to the multiple choice question. So the first one was, the first question was asked about number 3 on the multiple choice. So let's go to that. Give me a second. I'm gonna see if I can pull this up. So also, of course, I want to make sure that I'm looking at the right thing. So I'm assuming that you were on exam number 1, and we are talking about this question right here. Where's my live stream? Okay. So let's do this one. So if we have the graph of a continuous function that contains the origin, and we have this, then f of 9 equals this. So first off, this right here, again, should be tingling your calculus senses. And the reason I say that is that's a flashcard. That is actually the definition of a derivative. In other words, we took this function and we did this to it. What did we do? We took the derivative. What does that derivative equal? That. Okay? So what we're going to want to do is we're going to want to integrate this. Okay? We're going to want to integrate this function and recognize that it passes through the origin. In other words, recognize this function passes through the origin. Okay? So in this case, I'm going to clean things up a little bit so I have some room. I really don't have room here. Let's see what I can do here. So let's go and integrate this function. So I'm going to integrate this. Why can't I write? So this is x to the negative 1/2 dx. So when we integrate this, this becomes 2x to the 1/2 plus some c, and that equals some function. So like f, if you don't mind, I'm going to say equals y. And then what am I going to do? I'm going to plug in 0, 0 into this function because we know that this function passes through 0, 0. So I get 0 equals 2 times 0 to the 1/2 plus c. So it looks like c equals 0. So my actual function is y equals 2x to the 1/2. And then I'm just going to evaluate it at 9. So I'm going to go find y of 9. So that is 2 times 9 to the 1/2. 9 to the 1/2 is 3. So that's 2 times 3 is 6. So we get D. Okay? See if that makes sense. See if you have any follow-up questions on that. Again, that's a flashcard question. It's literally a flashcard question. So what does that tell us? We need to know our flashcards really well. And a lot of the multiple choice questions just straight out of the flashcards. They're basically asking a flashcard. So another question is coming in. So 1 over x is the derivative. Yes, that's correct. That is absolutely. So the question was asked, so is this piece right here the derivative of our original function? Yes, it is. So we took f, we did this to it, which means we took the derivative and we got this. So this right here is the derivative of f. That is exactly correct. Any other questions that you have in regards to the multiple choice packet so far? Again, if you don't, I understand that. I haven't really pushed it yet with you guys. I would say this. So we talked about at the beginning, the question was asked, hey, AP, they may not be doing, multiple choice this year or whatever. Is it worth it for us to do this? Should we just be spending our time on the free response? And I'm going to say, yes, I say that the multiple choice is worth it. And the reason is it's going to bring up, they're quick little ideas, and they're going to kind of bring up some of your weaknesses. So if you're like, ooh, I didn't recognize that as a flashcard. Well, it's kind of important that you recognize that as a flashcard. So it's not a direct review for the free response, but indirectly, there's a lot of good stuff that we can still get. There's a lot of kind of carryover or tie-in between the free response and the multiple choice, because a lot of times some of the multiple choice is very theoretical. Like this one. This was very theoretical. This was, look, hey, you had to recognize that we took a derivative. Okay? Any further questions that you guys have for me? And again, feel free if you want to jump to the voice channel and ask questions that way too. That is fine. It doesn't look like you guys have any further questions for me, because if not, then I am going to thank all of you for being here today. I will remind you that Monday at 10 a.m. we're going to be doing another question. In fact, let's just go look real quickly at what question we'll be looking at. If you want to look at it first before I go through it. I'm going to be going through, so whoop, that's not it. I'm going to be going through, nope, I have way too many things here. Okay, so we just did number 5. I'm asking you guys at home to do number 6. And then Monday, we're going to go through a brand new question, and that is number 7. Okay, so again, I do want to also remind you, I leave Discord open throughout the day. So if you want to pop in and ask a question, if you want to like jump into general chat and say something and scare the crap out of me, you're more than welcome to do that. I'm kidding. Please don't do that. But I do leave Discord open throughout the day. You are more than welcome to ask questions as you're going through. Okay. So again, thank you very much for your time. And I'm going to end this live stream. Oh, but it will be up on I will be again posting up on Discord and on the website.